by Dr. Kshitij. Let's see what does the term VLSI and technology means. In term VLSI, I stands for integrated circuits. That is number of components fabricated on a single semiconductor chip and joined together by a semiconductor wire. And the term VLS means very large scale. Here the scale signifies that within an integrated circuit the size can be scaled down, and the word technology means that there can be two ends of this VLSI. One is how a IC is fabricated, that is the technology part, and how the components on the ICs are connected, that is what is the topology of that IC, that is the design part. Now let's see what is VLSI system and why it is required. In any modern day gadget, whichever we see, there is a IC sitting inside it. May it be a cell phone, a digital camera, hearing aid, whether they are biomedical devices, computers or automobiles. There can be no modern day equipment without an IC. We cannot even think of our laptops, PDAs, computers, mobile phones. If we take out the ICs, all the systems will become useless. So now what are its application? VLSI is an implementation technology for electronic circuit, either analog or digital. It is concerned with forming a pattern of interconnected switches and gates on the surface of a crystal of semiconductor. Major ICs consist of microprocessors sitting inside personal computers, microcontrollers, memories like DRAM, SRAM, special purpose processors like ASICs inside CD players, DSP applications, or application specific instruction processors, or optical switches. This has made highly sophisticated control system mass producible, and therefore the devices based on ICs are comparatively cheaper. Now, why is the requirement of VLSI? The integration of components on a chip improves the design in terms of size, speed, power, and complexity. The complexity here is advantageous because as the complexity increases, the functionality on the IC will increase. So although from user point of view, we can say, or from designer point of view, we can say the complexity is a negative point or a negative trait, but from user point of view, complexity is good because on the same size of IC we are getting more functionality. Now let us consider a discrete circuit versus a IC. That is a comparison between discrete, that is separate components mounted on a PCB, and IC design. So the size in VLSI or IC design is some micron, whereas in discrete it is in millimeter or centimeters. The speed obviously will be higher in IC and it will be comparatively lower in discrete components. ICs has lower power consumption, whereas discrete components have higher power consumption. ICs are versatile. We have to simply change mass to change the design, but in discrete components they are not so much versatile. There is one advantage of discrete components, that they can be repaired. We can take out a single component and resolder another component in its place, but in IC design, once a component is broken or it's out of order, the whole IC becomes unusable and it cannot be repaired. ICs are low cost when produced in bulk, whereas discrete component based circuit is comparatively in higher cost. They are precise. Discrete components are less precise. ICs are more reliable due to there are no hanging wires or dry soldering issues in it. Less reliable due to soldering. Discrete components, it can work on low voltages. Discrete component requires comparatively more voltage. It can handle limited amount of power, whereas ICs can handle less power. Discrete component can handle more power than ICs. ICs are more susceptible to electrical interferences. Discrete components are less susceptible. And the speed required for modern day design issues is only possible through ICs rather than discrete circuits. Speed is comparatively less in discrete components, as the speed of silicon is no match for discrete components. In ICs there is well known component accuracy, and discrete component there is poor accuracy. Breadboarding of discrete components is possible before implementing an IC, whereas breadboarding is not possible in case of IC design. Parasitics are very important in IC design and they are to be included while designing an IC. They are not as much important in discrete component design. All components are not possible in IC design, whereas in discrete all components are possible. And simulation parameters and models vary widely, whereas model parameters in case of discrete components are well known. Complex circuitry on a chip may be used to obtain improved performance characteristics, but the performance of discrete component in comparison to IC is not so good. Now we'll see a brief evolution of microelectronics. The first transistor was developed in December 1947 in Bell Laboratories. As we know, Bardeen, Shockley and Brittain has developed it. First IC in 1960 by Fairchild by Jack Kilby. Moore's law. Gordon Moore, who was also the co-founder of Intel, predicted that the number of transistors per chip would grow exponentially. That is, they will double every 18 to 24 months. Now let's see the graph for the Gordon Moore. He is Gordon Moore. He is also the Intel co-founder and chairman emeritus. Now this is Moore's law given on the graph. We can see that here in 1970 the 4004 was the first microprocessor, and continuously on this graph we can see the number of transistors here on y-axis are doubling in approximately every 80 to 24 months. We can see here in Pentium there are 5 million transistors. In Pentium 2 there were 10 million, approximately 10 million. So the number of transistors on an IC, on the same side of IC, are doubling. So what was the reason, what was the cause of this evolution? Why suppose Moore has given this law, but what is the pressure, what is the parameters which are forcing the ICs to evolve? So this pressure or this parameters which results in the evolution of ICs are none other than the parameters enforced by the users. That is, the users require lesser size, more reliability, more power, more functionality, and more functionality, same size or lesser size. All those things exert a pressure on IC design and forces it to evolve, and we require to develop, or we require to develop more transistor or more components on the same chip. Now this is the integration level, SSI, MSI, LSI, VLSI, ULSI, GSI, that is giant scale integration, ultra large scale integration, very large scale integration, large scale integration, medium scale integration, small single scale integration. This shows logical gate count and production. So we started with the say 10 in SSI, and these were logic gates or registers. Then 100 to 1000, that is counter multiplexer adders. 1000 to 20,000 8-bit microprocessor ROM RAM. Then in VLSI 20,000 to 50,000, and above then ULSI, GSI in similar way. Now technology versus packing density. Technology means what is the basic construction, or what sits beside the inside the IC. So most comparatively metal oxide semiconductors have low power, high packing density. So CMOS is the ultimate solution. We are mostly using nowadays. We are using CMOS because of its higher power packing density and low power consumptions. BJT was the fastest. GaAs, that is gallium arsenide, for microwave applications and for fast applications. Now, as we have said that in Gordon Moore's law, that in every 18 to 24 months will have double the number of transistors on the same chip. So how this miniaturization of ICs is achieved? This is a typical MOSFET, that is source, drain, oxide, gate, and these are the contacts. So what we are reducing is, we are reducing channel length between source to drain of a MOSFET, or we can say we are reducing feature size, that is we are adjusting length as well as the width in accordance to the length. So this was the earlier size, and this is we have miniaturized it into 2, 4, 8, 16, And then number of this is the process which continues until date. The Gordon-Moore's law is valid, and every 18 to 24 months the number of transistors on the chip are doubling approximately. This is the top view of one of the transistors. This is a complete top view of the figure we have seen before. Now, what is a silicon chip? There might be a question arising. What is a silicon chip? It is nothing but a pattern of interconnected switches and gates on the surface of a crystal semiconductor, and typically this crystal is nothing but silicon. These switches and gates are made of areas of N-type, areas of P-type, areas of insulator, and lines of conductors joining areas together, that is forming a circuit, complete circuit. And the generally used conductors are aluminium, copper, titanium, molybdenum, polysilicon, and tungsten. The geometry of these areas is known as the layout of the chip, and that we study in the design portion. Connection from the chip to the outside world are made around the edge of the chip to facilitate connection to other devices. Now let's see a general view or animated view sort of thing of how a chip is made. So it starts with the same sand. Silicon is one of the most abundant element in the earth's crust. Sand, quartz has high percentage of silicon in the form of silicon dioxide. We can see it is all starts with sand, and it is the raw material for silicon is easily available, that is quartz. It is a comparatively more purified form of this silicon dioxide, and we can obtain silicon in molten form by using a arc furnace, and then we can get molten MGS, that is metallurgical grade silicon, from this quartz. So this is melted silicon. This is shown in a crucible, and we can purify this silicon melt. The resulting monocrystal is called ingot. This single crystal ingot is the molten MGS is converted by CVD process into EGS, that is electronic grade silicon, and the single crystal ingot or ball around approximately weighs 100 kilograms. It is 6 to 8 inches in diameter, and some modern technologies are, with help of modern technology now also we are able to produce 12 inches diameter ingots. It has silicon purity of 99.999%, and it is a single crystal structure produced either by Zokralaski method or by Bridgman technique. Now what we do, we slice this ingot by diamond saw blades into the discs called wafers, chips, substrate, die or base. Then these wafers are polished until they have flawless mirror smooth surface, and these wafers will start as the starting point for fabricating ICs. And now the question may arise, why we are using silicon as semiconductor, not germanium as the starting material. There are many reasons, and first two major reasons from the fabrication point of view. First of all, the material, that is the raw material for starting material for germanium, is not as easily available as the raw material for silicon. And second thing is the price of extracting germanium from the raw material is more higher than that of extracting silicon from the sand. And another important point is that the germanium exhibits high leakage current in comparison to that of silicon. It has narrow band gap, that is 0.66 electronic volts, whereas Si has band gap of 1.1 electronic volt. So therefore the germanium devices can operate up to 100 centigrade, whereas silicon can operate up to 150 degrees centigrade. Intrinsic resistivity of germanium is 47 ohm per centimeter. Silicon is 230,000 ohm per centimeter. And electronic grade silicon is more costly than EGS. Certain devices like high voltage rectifying devices and few infrared sensing devices are only possible with Si. Thank you for attending this lecture. We'll continue with more of IC technology introduction in next lectures.